Okay, so today we are going to discuss something about non-equilibrium Green's function and self-energy concept. Okay, so before going to these things, uh, we should give first the introduction about the Green's function and its simplification in the condensed matter physics. Okay, so Green's function is a mathematical physics concept which aims to solve some linear inhomogeneous differential equation. By linear inhomogeneous differential equation means by linear differential equation you know linear means the order may be anything but the degree should be 1. Degree should be 1, right? Degree should be 1, right? It is called the linear differential equation. Suppose we are going to take some example d2y dx2 plus sum of f of x equal to some okay, I'm writing here as y, so let me write here also f of x equal to some gx. What is this? It is a inhomogeneous linear differential equation. Why inhomogeneous? Because the right hand side is not equal to 0, rather it is a function of x and its degree is 1 and order is 2, right? So how to define the Green's function for that? Okay, so Green's function basically is a auxiliary function which is required to evaluate the actual function or our desired solution, right? Here we are interested to find the fx. So we used to consider another differential equation which is d2g x let me write x prime, sorry, dx2 plus this, nothing but this. So we can write fx to be g x prime gx prime dx. You can easily verify that it is a solution. How? Suppose you are converting this to d of fx equal to gx. Similarly, you can write this also d of g of x comma x prime is delta of x minus x prime. So take d on both sides. We can get d fx equal to d g x prime gx prime dx integration. What is this? Delta x minus x prime g x prime dx. What is the integration? It is nothing but gx, right? From the definition of the delta function. So you are getting the problem itself, the equation which we are interested to solve. So we can write that fx is a granted solution, right? So fx can be granted. So here we have expressed our solution in terms of the Green's function. So Green's function acts like an auxiliary function to derive the actual solution, right? By using the similar concept in quantum mechanics, you can write the Schrodinger equation IH9 del psi RT del T is nothing but minus h cross square by 2m z square psi RT plus V RT psi RT. So if we are interested to find psi, how can you express? By following the similar trend, we can write psi R T will be nothing but integration G R T R prime T prime psi R prime T prime this, right? You can see I had not written anything new. Just following the previous trend, I had written this because here there are two arguments R and T. So Green's function has the four arguments R T, R prime, T prime, right? Now what is the physical significance of Green's function? Now it is the time to see what is the physical implication of that. So we can see, or rather we can conclude on this expression that the Green's function is nothing but acts like a propagator which is used to propagate the wave function from a previous position R prime T prime to a final RT T time R position. Okay, so it is basically acts like a propagator, right? Next, following this similar trend, Feynman later in 1960s or something, he mentioned the field propagation, quantum field propagator, which is associated with the Green's function and can be easily expressed as G R T R prime T prime to be equal to minus of iota time ordering psi RT psi dagger RT. Now you might get confused what is psi and psi dagger. These are nothing but the creation and annihilation operator, field operator, right? So in case of fermions, you can easily express this thing in terms of the creation annihilation operator, like we can write G, and these are all matrices, like so. Now we are writing the ith row jth column, that is the ij component, component of the matrix or ijth element of the matrix, and sometimes it is known as causal Green's function, that is sometimes it used to be as prefix C because it encodes the cause effect structure in time evolution. So we might omit this C. Okay, so Gij basically we are going to write. For fermions or rather electrons, we can write in terms of time coordinate I, time ordering. For fermions it is anti-commutation Ci T Ci dagger Cj dagger T prime. What does it imply? It implies we are creating we had created a particle at T prime and we had annihilated one particle at time T, or rather we can say that we had reduced one antiparticle at time T prime at past, and we have introduced one antiparticle after some later time. So it can be expressed as theta t minus t prime in terms of step function Ci Cit this this thing. What does it imply? If t greater than t prime, then this term only exists, and if t prime greater than t, this term will exist. So we can express this to be okay. This is the Gij retarded minus Gij advance. What do we mean by retarded and advance? Retarded means the t is at time t prime you have perturbed the system, and after time t you are going to see some effects for the perturbation. That is, we are going to see the implication of the, or rather than the response of the perturbation after some time t, and at time t prime we had made some perturbation. And what does the second term represent? The advance. That is, we have measured the we are going to see the response of the system after making the perturbation at some future time, which is very unphysical. So we are not interested about this advanced Green's function, right? Rather, it is basically convenient that you are going to study the system after making the perturbation itself. That is, we are going to see the response of the system after making the perturbation to some past time. Okay, and it can be noted that the Gij retarded is always conjugate of Gij advance, as can be obtained, right? Next, let us write the retarded Green's function. So Gij retarded means minus iota theta t minus t prime expectation anti-commutation ci e cj t prime. This. So we can simplify this thing by minus iota theta t minus t prime expectation ci e cj derivative minus iota theta t minus t prime cj derivative ci t. Right? It is known as the theta t minus t prime g greater minus g lesser. What is greater and lesser? So g greater is defined as minus iota ci t cj dagger. Basically it is also ij. T prime this, and lesser means, don't get confused this I and this I. Okay, this is imaginary I. This one. Right? Plus. So now the lesser Green's function gives us the number density, right? So we can calculate the number operator, this like minus I g less. This is one important physical significance. Okay. So these are the definitions of the Green's function that all are required for the Green's function approach, right? These all the basic definitions which we will use later in our discussion. Okay, so let us proceed further. Why we are interested to discuss this thing, right? So basically we want to study some physical properties of a system. Suppose you have one device like this and you want to calculate the conductivity corresponding to the system. Now suppose you have a conductor here. Suppose this is your conductor and you are going to measure the conductivity corresponding to it. So how you will measure? You will just probe it, right? You will have two probes and the conduction of the electrons from these barriers, it will just indicate the currents as well as by the application of the external voltage the charge carriers will move and you will just able to get the resistance, conductivity, etc, etc. But for that the basic thing you need to connect the leads to the system, right? Now here lies the problem. So your conductor has some Hamiltonian like this. Suppose I am giving it HC or HD. For device I am HD I can write. This is the left lead, this is the right lead. Okay. So let us do first basic example, then we will do this three terminal devices. Okay. Suppose you have only one probe, just like this side, and you have one system here like this. Okay. So here are the lattice-sides. Here are the lattice-sides corresponding to the probe. Now probe you used to consider one crystalline structure which has a unit cell arranged regularly to make the whole crystal, right? So this is nothing but the primary assumption is every site is coupled individually. Like this is a p site is coupled with the I site and no other inter combinations are possible. Like this side will not be coupled to this side will not be coupled to this, and so on. Okay, it is a basic assumption. So how you will write the Green's function corresponding to this system? First of all, now the system you had considered, the system Hamiltonian H contains some it will be a matrix definitely, but it will include the submatrices. Why? Because it will include the device Hamiltonian HD, the lead Hamiltonian HL, as well as the coupling between the lead and the system. If I denote this to be tau, for making it to be Hermitian, it should be tau diagram, right? This is our basic Hamiltonian. The Hamiltonian matrix itself composed of the matrix which is made of some submatrices HL, HD, tau. Here HL and HD are the square matrices, but the tau are the rectangular matrices, right? Because the dimension of the lead and system may vary. How you will solve the Green's function? So you will just write the retarded Green's function following the definition, that it would be nothing but inverse of E plus iota eta. Now why iota eta is applied here? To convergent, to make the integral of the Green's function convergent, we introduce this infinitesimal positive number eta, which is imaginary. Okay, so eta is real and iota eta is imaginary. So we are going to introduce this eta to make the integral corresponding to the Green's function to be convergent. Otherwise it will just blow off, and the condition of the Green's function is minus infinity and plus infinity. It should go to G should go to 0. To make it convergent, we are going to introduce this eta. So now this is a matrix, so it will be multiplied by identity minus of Hamiltonian inverse. Now how to calculate this? So since our Hamiltonian is divided into some submatrices, our Green's function will also be divided into submatrices. So we can write this to be G. For probe we are writing P. For device we are writing GD. And this is the, I'm giving it to be left, right? So we can write this to be L. Nothing problem. So LD. This is GDL equal to E minus iota eta E plus iota eta I minus, what was it, HL. Now for device we don't need to consider the eta because your device is some finite size, okay, but your probe is, I have not mentioned the other boundary, right? So your probe is infinite dimension, so you don't know whether the Green's function should converge or not. So for that you should need to consider the eta part. For device it is finite size, that's why we are not interested to consider this eta. So it's simply HD, right? This is nothing but tau. This is nothing but tau dagger, right? Inverse. What we can write now? We can take the Hamiltonian to this side and solve it. So E minus E plus iota eta I minus HL tau dagger. This is tau. This is E I HD multiplied with the Green's function will be this, right? Now if we simplify, what we will get? Let us focus this part. So we will write E plus iota eta minus HL times G LD. We are writing this part, okay? Plus tau GD equal to, so this will be 0, right? This part, and tau dagger GL or tau dagger GL plus tau dagger GL EI. We will not calculate unnecessary calculation, that's why we are thinking to calculate, okay? So this is GDL equal to nothing but pi. Okay, from here what we can get from this equation, let us write this to be 3, this to be 4. So from 3 we can write basically GLD equal to minus tau GD and this 1 divided by B this. So this whole quantity can be think of to be another Green's function. minus G for lead, G for lead, retarded, tau G T, right, where your G L R, what is this, 1 by, or rather we can write in terms of inverse, so E plus iota eta I minus H inverse. What is this? This is the self Green's function or isolated Green's function corresponding to the lead, right? So now what you can do, you can write the GLD means GDL, right? Right. So now what we will do, your GLD is this. Now you can easily get GD. So your GLD can be written as E plus iota eta r minus HL. GLD means minus GL r tau. This plus tau. GD. Or okay, we had calculated this column, right? So if we calculate the second column only, what we will get, let us see. So this thing will be, for second column this is LD and this is GD, right? So from this we can easily get GD. Okay. So now from this 4 equation you can write tau dagger GLD means minus GL or tau this and plus EI minus HD GD equal to I. So we will get GD to be EI minus HD minus tau dagger GLR tau. This is the Green's function corresponding to the device due to the coupling of the lead. Now why it is called non-equilibrium Green's function? Because in our previous cases we does not imply anything connected to the system, but here we have connected the lead to the system so that our number density is not fixed. It is continuously flowing, the charge carriers are flowing from the lead to the conductor. If we imply, now if we took this red color generalization, now we can write easily that for this case we also get okay, let me once simplify this thing, that this last factor which we have mentioned here, the coupling dagger GLR coupling matrix is known as the self energy corresponding to the lead. So GD will be minus HD minus self energy. Now if we consider this case that we had mentioned earlier, it is connected to the two leads, left and right. This is the conductor. Here the GD will be E minus HE minus sigma L minus sigma R inverse, right? Where sigma L is tau dagger GLR tau, and this is some another coupling matrix, and the two are same unit cells, so we can take this coupling matrix to be same GR. Let us write this to be smaller. This. Okay. So these are the self energies corresponding to the leap. Now what are the physical significance? The self energy implies that since the leads are infinite, we have a infinite dimensional matrices, but it is impossible to calculate the infinite dimensional matrices. So we are focusing only to isolated Green's function that corresponds to the connected region only. But we should take care about this semi-infinite portion contribution also, right? So this thing is coming from the self energy part. Now again, the self energy part contribution is something tricky. Why? Because here also the self energy will correspond to the infinite portion, right? So for this infinite portion to take care into account, we used to consider only the nearest neighbor conduction. For nearest neighbor conduction, we can write this tau dagger GLR tau. Ijth component will be nothing but some t squared. If t with a strength, hopping strength, then t square, because it will produce some real value t square. T star t will be t square, and GLR will be nothing but G corresponding to Pi Pj, because Pi is only connected to the ith side and Pj is only connected to the pjth side. So these elements will only survive, other elements will be zero only. So we don't need to take bother about the infinite dimensional structure. So this is the basic procedure to calculate the Green's function corresponding to the device. Now what are the application of this? Once you will get this, you will just define this to be a broadening matrix, which is defined as iota times sigma L minus sigma L dagger. Also the right broadening matrix sigma R sigma R dagger, and you will able to write this transmission function to be equal to trace of gamma L GT dagger gamma R GT. Now once you have calculated this transmission matrix, you will just put this to the conduction formula. Here G is not the Green's function, okay? Here G is not the Green's function. What I should write? Suppose C, conductivity C is E squared by H P. You will get the conductivity by this. Okay, these are the procedure. To get the conductivity of the system, we have to devise the Green's function corresponding to the device. But for Green's function corresponding to the device, we have to connect the leads, but leads are semi-infinite. That is, one portion is finite, but the other portion is infinite. So we have to need to take care about the self-energy contribution, and this self-energy contribution can be coming from the isolated Green's function, which we have mentioned here, and as well as a coupling matrix.